what if the future of I mean, the real future, isn't just about building these massive models? What if it's about AIs that can learn to code autonomously?
That's a huge question.
Right. So today we're doing a deep dive into, well, the journey of large language models, LLMs, and how this thing called reinforcement learning is maybe paving the way for coding systems that truly run themselves.
And it's potentially a massive breakthrough. Some researchers see this as like the foundation for building actual superintelligence.
Exactly. We're going to unpack insights from a real leader in LLM research. We'll look at why this is seen as the root node problem for AI and how we might be entering a whole new phase, an era of experience in AI. It sounds like a fundamental shift in how these things learn from the real world.
Yeah, absolutely. Our mission here really is to understand why autonomous coding keeps coming up as this root node problem.
Okay.
Think about it. If an AI can learn to program itself, then it can build, iterate, improve itself, improve other AIs. You know,
Ah, right. It becomes the building block.
it becomes the fundamental building block for whatever comes next. Yeah.
Yeah.
And we'll definitely explore this era of experience and what that really means for how AI learns.
Okay, let's unpack that. So if you think back maybe around 2020, there was this huge shift, right?
Yeah. The scaling laws paper.
That's the one.
Yeah.
The breakthrough paper on scaling laws for large language models. And the core idea, it seemed simple, but wow, the impact
It was basically more compute, more data, bigger models.
equals way better performance, but not just better, right? It unlocked these new, sometimes kind of unpredictable skills. Like they were starting to, I don't know, think.
That's the fascinating part. They didn't just get better at what they were trained on. They started to generalize. You saw this continuous improvement across benchmarks.
And this emergent behavior stuff.
Exactly, which leads right into things like chain of thought or CoT prompting.
Hmm.
That was really noticeable with models like Calm around 2021.
Right, chain of thought. Explain that a bit.
So the incredible thing was, if you just ask the model to show its work, essentially, to think step by step, accuracy on really complex problems shot up. Middle school math problems were the classic example.
Okay.
Ask for the answer, it might get it wrong. Ask it to lay out the reasoning first, and suddenly, boom, correct answer.
Wow, just by asking it to show the steps.
Yeah, and it wasn't just math. It worked across loads of areas, Q&A in different languages, puzzles, NLU tasks. It was a big deal.
So that reasoning ability, that CoT prompting, that's what really enabled the chatbots we all use now, like ChatGPT, Gemini.
Pretty much. That leap in reasoning and instruction following was key. But there was another piece needed for interaction.
Which was,
RLHF, reinforcement learning with human feedback. That was absolutely crucial for making chatbots work the way they do.
right, RLHF, teaching the models what humans prefer.
Exactly, using lots of human feedback data to guide the model's responses. And interestingly, that same idea, RLHF, it also shows real performance improvements when you apply it to generating code.
Okay, so models are getting smarter, reasoning better, even learning from feedback.
Right.
But then there's the cost.
Oh, the cost. Yeah.
Training these things it's astronomical. You hear figures like tens of millions of dollars for one model.
Mm-hmm. It's massive.
So last year, people started asking, are we kind of hitting the wall? Can we keep getting gains just by making models bigger and bigger given the cost?
That was a huge debate. And still is, to some extent.
Especially because using the models, inference, that's relatively cheap compared to training. So the question becomes, if pre-training scaling is getting prohibitively expensive, where do the improvements come from?
That's a great question. And it forced a shift in thinking, really, towards focusing on scaling compute at inference time, using the models more cleverly, basically.
Okay.
Two main ideas sort of popped up. First was majority voting, sometimes called self-consistency.
Right. Ask the model the same question multiple times and pick the most common answer.
Essentially, yeah. Generate multiple possible solutions and then vote on them. The other one was sequential revision.
Like asking the model to check its own homework.
Kind of. It's like how we humans might write something, then reread and correct it. You let the model revise its previous outputs, iterate on its own answers.
Okay.
And this often leads to much longer, more coherent reasoning chains and, crucially, consistent improvements in accuracy. And here's the key part. These inference time tricks, they show very clear gains in areas where you have solid automated verification.
Ah, okay. So where you can actually check if the answer is right automatically.
Exactly. Think math problems, you can use a calculator, or formal proofs for coding.
Unit tests. Compilers.
Precisely. Unit tests, execution environments, compilers like PyTorch. You can run the code and see if it works, if it passes the tests. That ability to verify automatically, that translates directly into measurable intelligence gains for the model at inference time.
That makes a lot of sense. If you can check the answer easily, these methods work great. But why isn't that the whole story then? If it works so well, why isn't everyone just doing inference time scaling? It sounds a bit too easy or maybe just too slow.
That's the catch. It's a critical limitation. These methods are great at finding a correct solution that the model might be able to produce. But they often require sampling a lot. I mean, a lot. The correct answer might be very rare among all the things the model generates.
So you might have to ask it thousands of times.
You might need to sample, maybe 10,000 times just to find one correct solution for a hard problem.
Wow.
So you find the needle in the haystack. But the process doesn't teach the model how to make needles or avoid haystacks during its actual training. It's just a clever way to sift through the hay after the model's already trained.
Okay, that clarifies the limit. You find the answer, but the model isn't fundamentally getting better at generating correct answers from the start.
Exactly. Which brings us to the next big idea.
The next frontier. So if just using models smarter has limits, people started looking back at the training process itself.
Right. The question became, if RLHF worked for chatbots, using human feedback, could we use reinforcement learning, but with automated feedback during training, especially for things like math and code where we have that automated verification?
So using the unit tests or the math checker, not just at inference time, but somehow feeding that back into the learning process itself.
Precisely. And this leads to the question, why is reinforcement learning, RL, seen by many now as the next frontier for scaling AI performance?
Okay, why?
Well, pioneers in RL, folks like David Silver, Richard Sutton, they talk about entering the era of experience.
The era of experience, what does that mean compared to what came before?
So think about it in phases. First, maybe you had the era of simulation. Like AlphaGo, the rules of the game, the world model were perfectly known. You could simulate perfectly.
Okay, AlphaGo and its simulated Go world.
Then came the, let's call it, era of RL using human data. That's the RLHF we talked about for chatbots,
right,
using human preferences as the signal. But this era of experience, that's about the AI engaging directly with the environment, maybe the real world, or a complex simulation, like a coding environment, where things are messy.
Messy how?
Well, the feedback isn't always perfect. The data isn't nicely curated or complete. You will have imperfect things. It's not just clear success or failure all the time.
Like learning in the real world, basically.
Kind of like learning to ride a bike, yeah. You wobble, you might fall, you get scraped knees, it's all feedback.
Yeah.
It's imperfect, real-time interaction that drives the learning. The model has to learn from that direct, often messy experience. And we're seeing proof this works, especially in math again. Using RL during training, feeding back results from verifiers, allows training time compute to push accuracy higher on tough benchmarks, like the AMY benchmark.
So unlike just making the model bigger, which seemed to plateau.
Right. This RL approach seems to break through that saturation, suggesting it's a genuinely new way to improve performance by learning from interaction.
Okay, this sounds huge. A new paradigm almost. But if RL is this promising path forward, why isn't everyone just, doing it already? It sounds powerful, but maybe really hard.
Oh, it's definitely hard. There are major challenges with scaling RL effectively.
Like what?
Well, first, the whole system stack. It's not just one model anymore. It's this complex machine learning plus system stack.
Meaning
you often need multiple copies of different models running together. Think about algorithms like PPO, requires maybe 4 models. DPO, like in DeepSeek Map, maybe 3 models.
all running simultaneously.
Yeah, often needing different models like actors, critics, reward models, reference models, all interacting on potentially huge clusters of GPUs. Getting that all to work efficiently, keeping utilization high. It's extremely hard from a systems engineering perspective.
Okay, so the engineering is tough. What about the AI side?
The big one there is reward hacking. If you're using, say, another neural network to predict a reward because you don't have perfect verification, the main AI can get really good at tricking the reward model into giving it high scores without actually solving the real problem. It learns to hack the reward signal itself.
Ah, like finding a loophole in the rules.
Exactly, which is why...
Why coding is such a good fit.
Precisely. This is why autonomous coding is a great domain for scaling RL, because it has that strong, built-in automated verification.
The unit tests, the execution feedback.
Right. Execution feedback, unit tests, metrics like sweet bench scores. These provide clear, objective, hard-to-hack feedback on whether the code actually works.
So you can design much better reward functions.
Exactly. It massively reduces that reward hacking problem because the reward is tied to actual verifiable outcomes. Does the code compile? Does it pass the tests? Does it run correctly?
Okay, so the verification makes coding the ideal test bed for pushing this RL approach forward. So bringing it all together, what's the bigger picture here for real-world impact? Where is this heading?
Well, it ties right back to that initial idea. Companies like Reflection AI, for instance, state their mission is building superintelligence.
And they see coding as the starting point.
They see autonomous coding as the root node problem. They understand that just generating a snippet of code isn't enough. That's only one tiny piece.
Right. Software engineering is way more than just writing code.
Absolutely. The real goal is to generalize these AI systems across end-to-end workflows. Think about the entire software development lifecycle requirements: design, coding, testing, deployment, maintenance.
So automating the whole process, not just the typing part.
That's the ultimate vision, yeah. Using coding as the beachhead to build systems that can handle complex multi-step tasks autonomously.
Wow, what an incredible journey we've just covered. Seriously, from those basic scaling laws that kind of kicked off this whole modern LLM wave, all the way to this cutting-edge use of reinforcement learning, trying to get AI to actually learn from experience in coding environments. It really feels like we're just scratching the surface.
It does. And if this era of experience really is taking hold, if AI truly starts learning effectively from direct, sometimes messy, real-world interaction, just think about how that fundamental shift could change things. Not just how we code, obviously, but maybe how we approach and solve complex problems in, well, almost every field you can imagine.
That's a huge thought. What does that mean for you listening right now? For your own learning, your own work, where could this lead?
Definitely something to chew on.